Hello, welcome to Engineers Mindset. So in the previous video, we were able to derive the basic equation of bending. Now in this video, we are going to apply this equation towards solving problems. So let's consider the problem on the board. It says a 250 millimeter depth by 150 millimeter width rectangular beam is subjected to maximum bending of 750 kilonewtons meter. Question says determine I, the maximum stress in the bar, II, if the value of E, that's Young's modulus, for the beam material is 200 giganewtons per meter squared. Find out the radius of curvature for the position of the beam when bending is maximum. I said the value of the longitudinal stress at a distance of 65 millimeter from the top surface of the beam. Okay, so let's try to draw the diagram and see what they say. So we have a rectangular beam. Okay, so of course it's something like this, a rectangle. All right, so question says that, okay, the depth of the rectangle is what? 250 millimeter. So depth is simply 250 millimeter, which is simply from this top to here is the depth. It was given as 250 millimeter. We are given the width is 150 millimeter. So from here, okay, let's take it down. From here to this point is still the same thing. It's simply 150 millimeter. So this is a rectangular bar. Now the question says we were given that bending is maximum. Okay. All right. So they said okay. So we are given that the beam is subjected to maximum bending of 750 kilonewtons meter. So which means maximum bending moment max is simply what? 750 kilonewtons meter. It was given to us already. All right, so we are asked to find the maximum stress in the what? In the beam. Okay, so we're asked to find the maximum stress in the beam. Now we come from bending the equation. Okay, we have that M all over I is simply equal to, we have Young's modulus all over R, and we said it's also equal to the stress divided by the what? Distance from the neutral axis or from any point on the beam. That's what Y is. So the first part of the question, we are given maximum bending moment of 750 kilonewtons. We are asked to find what? The maximum stress. And we are asked, okay, we are asked to find the maximum stress. And this section is a rectangular section. This I here stands for what? Moment of inertia. It means now I know the moment. I also know the moment of inertia. I know the stress. This is what I'm asked to find. And I know the distance about your bending is maximum. So I said in the previous video when I was deriving the basic equation for bending, I said that bending is maximum always at the neutral axis. And the neutral axis is simply what? Dividing this into two. That's the middle point. So from top to the bottom, we simply have y over 2 or d over 2, sorry. So this is simply the neutral axis, or from this point to this point, d over 2. That's the neutral axis. That is where bending becomes maximum. At the middle of the beam is where bending becomes maximum. And that middle is simply what? Middle of the depth of the beam. Okay, so that's where bending becomes maximum. So we can find I, of course, moment of inertia for a rectangular section is known. Okay, so all we need to do now is what? Only use these two parts of the equation that we know. They are asking us to find stress, so automatically we have to use this equation, and we have to use this equation. So therefore, we are simply going to make use of M equal to what? Okay, so we just pick out what? These two, and we are simply going to have M all over I to now be equal to stress all over Y. So we use these two equations, okay? So whenever a problem is given to you on bending, all you need to do is look at the three equations. Since the equation is actually what? 3 in number, look at the three equations and try to make sense with what? Any two that conveys what you're looking for. or contains what you're looking for. You solve with that tool. In the question, I was given a maximum bending moment, so that can stand for the moment. I know how to find what my moment of inertia because it's actually a rectangular section, and I'm looking for the stress itself. So which means I can only what relate these two and not the middle one. Okay, so let's try it now and see. So here, if moment is maximum here, it also means the stress here has to be maximum. So this equation can be written as maximum moment M max all over moment of inertia I, and that's simply equal to, of course, the stress will become maximum stress at maximum moment. And of course, we are going to have what? The maximum distance from the neutral axis. That is where bending is maximum. Okay, so Y max I've said is going to be what? Distance or the middle point of what? The depth. That is where bending moment is maximum. That's at the neutral axis. Y max is simply D all over 2. And this is equal to D is the depth, which is 250 millimeter. So we simply have 250, okay, divided by 2. And this is actually equal to, okay, that gives us 125 millimeters. So let's convert this to meters now. This simply implies that Y max, okay, is simply equal to convert this to meters, simply divide by 1000. We are simply going to have 0.125 in meters. So that gives us the value of what? The maximum distance or the distance about the neutral point where bending moment is actually maximum. Okay. Okay, so having gotten this now, next is to find the moment of inertia, I. Moment of inertia for a rectangular section is simply what? B D cube all over 12. And this is equal to, B here stands for the width, and the width was given as 150 millimeters. So please take note, we have to convert all this to meters. 150 millimeter to meter is simply 150 divided by 1000. That will simply give us 0.15 meters. Okay. Same thing here, we need to convert this to meters. 250 millimeter to meter simply means 250 divided by 1000. That will simply give us 0.25 in meters. So we need to convert all towards meters. Okay, so the moment of inertia now becomes, B is the width and the width is 0.15. So we simply have 0.15 multiplied by D is the depth, and the depth now is 0.25. So remember here depth cube. So it simply becomes 0.25 to the power of what? 3 all over 12. Okay. All right. So moment of inertia I is now equal to, so this becomes 0.15 multiplied by, so 0.25 to the power of 3. That gives us 0.015625 all over 12. Okay, so I, which is moment of inertia, is equal to, so 0.15 multiplied by 0.015625. We have 0.00234375. Okay, all over 12. Okay. Okay, so if we divide this now by 12, we are going to obtain that moment of inertia I is now equal to, that gives us 0.000195,312 in meters 4. So that is the moment of inertia. So next thing to do is simply what, from the equation, okay, so here, so we have moment of inertia, we know the maximum bending moment, we know the maximum distance. So all we need to do is simply make maximum stress the subject of the formula. So we can simply obtain that sigma max, okay, from this equation now, we can find out that sigma max is simply what? If we cross multiply, Y max multiplies by maximum bending moment, that simply gives us M max, okay, multiplied by Y max all over what? The moment of inertia I. So simply all over I. So we have this. So we can simply say sigma max, which is the maximum stress, what we are looking for, is now equal to maximum bending moment was given from the question as 750, okay, 750 kilonewtons meter. It was given from the question. So we simply have 750 times kilo means times 10 to the power of 3. Okay, so times 10 to the power of 3. Okay, multiplied by y max, which is the distance from neutral axis. It was given as what? 0.125 meters. So we have 0.125 all over the moment of inertia. We obtain that to be this, which is simply 0.000, okay, 195, okay, 312. That gives us a moment of inertia. So from here, we can obtain the value for the maximum stress induced in the bar. Okay, let's do that and see. Okay, so that simply gives us that moment M. So that gives us that the maximum stress sigma max is now equal to, we have that value to be 93750. 93750 divides by value for what? Moment of inertia, which is 0.00019, okay, 5312. All right, so this simply implies that the maximum stress is equal to 48000, okay, 1228. This is newtons per meter squared. All right, so we can approximate this to simply be converting this to meganewton. Sigma mass is simply, let's move decimal places back, 1 2 3 4 5 6. So we can simply have that to be, okay, this is 0.8, 0.8, so 1 2 3 4 5 6, that's around 48 mega newtons per meter squared. Okay, so that simply gives us the value for the maximum stress induced. All right, so if you know this value now, that part is settled. The next part of the question says we should find the radius of curvature, find out the radius of curvature for the portion of the beam when bending is maximum. So see what at maximum bending moment. This time around, we're given the value for Young's modulus as 200 giganewtons per meter squared. Okay, so we're going to now employ from the moment equation again, from the bending equation again, recall we said M over I is equal to E all over R, and that's equal to simply the stress, okay, stress all over Y. All right, so this time around, we are being asked to find the radius of curvature. So you can either choose these two equations or you can choose these two equations. Whichever equation you choose, you're going to obtain the same result or the same answer. All right, so let's simply choose these two, M over I. So from M over I, okay, over I equals E over R. All right, so we simply have this. Now let's employ this equation now to solve. We know M, which is the moment. We know I, which is the moment of inertia. We also know what Young's modulus is now. We are giving Young's modulus as simply 200 giganewtons per meter squared. All right, so we can now make radius of curvature subject. And if we do that, we are going to obtain that radius of curvature is simply equal to, by cross multiplying, I multiplied by E gives us EI, which is also known as flexural rigidity, all over M, okay, all over M. M stands for what? Stands the maximum moment. In this case, it's going to be M max. Okay, so we know the Young's modulus, we know the moment of inertia, we know the maximum moment, so we can find the radius of curvature. All right, so from here now, R is now equal to Young's modulus was given as 200 giganewtons. So this is simply 200. Giga simply means times 10 to the power of 9. Okay, multiplied by the moment of inertia itself was given as this, which is 0.000 we have 195, okay, 195,312. All right, all of this divides by the value of the maximum moment, and the maximum moment was given from the question as 750 kilonewtons meter. So we simply have 750 kilo means times 10 to the power of 3. Okay, so radius of curvature is now equal to, so we obtain this multiple. That gives us 39062, okay, 400, 0. All right, all over 750 times 10 to the power of 3. So therefore, we can obtain the radius of curvature as simply divide 750 exponential 3. Okay, that gives us 520832. 520822 in meters. So this becomes the radius of curvature for the material. Okay. Final question says find the value of the longitudinal stress at a distance of 65 millimeter from the top surface of the beam. Okay, so what that simply means is that from the top surface, simply measure out 65 millimeters, so somewhere around here. So this becomes the new value for y. So all they are asking us to do is simply what? Replace the value of y with what? 65 millimeter. That becomes distance from the top surface to what? Any point on the beam. So we have that to be 65 millimeter. That gives us the value for y. And we are asked to what? Find the stress at what? This distance. So we still employ the bending equation. All right. So from the bending equation, all right, so we simply have m over I equals E all over R equals stress all over Y. So now they've given us a value for Y at 65 millimeter from the top, simply means that Y equals 65 millimeters. So if we convert this to meters, this simply implies that Y is actually equal to, simply divide 65 by 1000. That will give us 0.065 in meters. That gives us the distance from the top surface. Okay. Okay, so we'll have that to be the distance from the top surface, 0.065 in meters. Okay, so if we've known that now, of course, we are looking for the stress. We know this, so we know the moment, we know our moment of inertia. So we can use any of the equation. We can as well relate these two, since we know Young's modulus and we know radius of curvature now, so we can use any of the equations. So let's simply use this and this. From E over R, okay, Young's modulus all over radius of curvature equals stress all over Y. We simply make stress subject. If you make stress subject, you're going to have sigma is equal to simply what? E multiplied by Y. So if you cross multiply, Y multiplies E all over R. Okay, that's EY over R. So this simply means now that the stress about that portion is simply equal to, Young's modulus was given as 200 giganewton. So once again, giga simply means 200 by 10 to the power of 9. Okay, multiplied by Y, distance of 65 millimeter, which will obtain to be 0.065. So this is simply multiplied by 0.065 in meters all over the radius of curvature. Radius of curvature was obtained as this, 520822. Okay, 520822. All right, so stress is now equal to, that gives us 1.3 by 10 to the power of, okay, times 10 to the power of 10 all over 520822. Okay, All right, so if we divide that now, we can obtain the stress about that portion. Simply sigma is now equal to, so divide 5 to 0.822. Okay, so we have 249 6854 3.19 newtons per meter square. So we can approximate this, take it to 1 2 3 4 5 6. So we can simply call stress to be equal to, so move decimal point 6 steps backwards, 1 2 3 4 5 6. It gives us 24.97 mega newtons per meter squared. Okay, so that's how you employ the bending equation to solve problems. So I will see you in the next video with more problems on bending equation. All right, guys, thanks and cheers.